Hello. This is the introduction to a webinar series that support the course Grazing Incident Scattering, a tool for probing the lateral structure of thin films and layers. This course is held by Malmo University, supported by LINX, the Lund Institute of Advanced Neutron and X-ray Science. The lecturers in the course are Marite and Felix, who both come from the Biomedical Science Department at Malmo University. Juan, who will be presenting some modelling software, is based in Garching near Munich. He's actually part of the Jülich Centre for Neutron Science. Myself, Chris Garvey, I'm also in the Biomedical Science Department at Malmo University. I'm also supported by LINX, and I'm currently on secondment from Australia. In very broad strokes, the aims for this course are, first of all, to know what kind of scientific problems are appropriate for the technique of grazing incidence small angle scattering. This is really about you defining what kind of scientific question you have in mind and whether GISAS is the appropriate method of answering the question. We'll look at the kinds of samples that you need to get useful information from the GISAS experiment. We'll talk about the experiment, and I'll be using the example of a new Xenox Zeus instrument, and we'll use that to provide data for web meetings and discuss that. We'll also show you how to manipulate the data with a free piece of software, and all this is aimed at you analysing the data or having the expertise to analyse data that you make yourself in your own scientific problems. Overall, there's 11 lectures/webinars. This is, of course, the first one. They're all about 20 minutes each. We keep it in sort of small, digestible bits, which have been broken down into sort of more or less sensible stories. So the course itself will take the form of these webinars. There'll also be some web meetings which have been outlined in your the acceptance letter that you got. These web meetings will be the opportunity to ask questions based around the lectures. We'll be able to give demonstration and guidance on using Fit2D, which is the software that we're going to give you for the assessment task to extract some useful information from some data that we'll give you. We'll also use it to give a lot more working knowledge of the software Born Again, which is modelling software for GISAS experiments. And also, of course, which is really quite important in small angle scattering, is how to integrate small angle scattering and other experimental techniques to give an overall picture. At the end of the course, we have a very simple assessment task, and this will be necessary to get the full benefit from the course. We'll give you some sample data to evaluate. This will be 2D detector images. We'd like you to extract some appropriate 1D data from that and use this to assign appropriate unit cell and characteristic length scales with errors. So it's a very clear-cut task. We just use this to demonstrate, to allow you to demonstrate that you understand the technique. So in this first lecture or webinar, I'd like to introduce the technique of grazing incidence small angle scattering to you. And really the overall aim of this lecture is to understand what scientific problems are appropriate for the grazing incident technique. So this lecture or webinar really asks the question of why do the experiment? and look at the kind of information you get from the GISAS experiment and the limitations of that. And I'll do that through a few examples, 4 to be precise. I'll also briefly introduce, and we'll expand on this later in the course, how we measure and what we measure, and importantly, also start the discussion about how we extract information from these particular experiments. Okay, so let's think about GSAS. Cake is the usual metaphor for understanding the kind of information that you get from a GSAS experiment. So you have a structure, an overall structure, and inside that there's layers and organization of those layers, and maybe importantly for the GSAS experiment, organization within the layers themselves. The GSAS experiment is, in a sense, a visualization of the layers and the structures buried within the cake. We're able to obtain this information non-destructively, and it's a statistical information, unlike the slice that you take out of the cake where you can see everything. It's non-destructive, and you're sampling over your entire cake. So without slicing it, you know what's inside. There's some special possibilities within the GSAS experiment. One can focus on particular aspects of the structure with different forms of contrast, whether that be deuteration in the case of neutrons and magnetic contrast in the case of neutrons. There's some contrast techniques which are available with soft X-rays, which we'll briefly touch upon. The other extremely powerful possibility with this technique is in situ or in operando measurements. So we have some structure evolving over time as we measure. And I'll also give a few examples of that. So some examples of the kinds of information that we can get from a GSAS experiment. These are in decreasing length scales. So in the first case, we have some real space pictures of some block copolymers which have self-assembled on a surface. These block copolymers will assemble into different morphologies depending on how they've been exposed to vapor, solvent vapor, or different block structures. And one can see in the real space measurement that they're either cylinders or lamella, and both give very clear and clearly defined GSAS patterns there on the left. But if you're looking at the processing of them, it's impossible to slice them up as you go along. So what the grazing incidence technique allows you to do is to look at what happens as you treat the film and the kind of morphologies that relate. The second example that I have comes from membrane biophysics, and in this case the workers wanted to reconstitute a protein which is implicated in membrane fusion, and they were doing this with different kinds of lipids on a substrate. They had the protein dissolved in a surfactant, and they wanted to look at how the surfactant affected the structure as well as how the protein affected the structure, and that's really quite a nice piece of work. In this case, they looked at the packing of the lipids in bilayers and how the bilayers themselves were arranged. So, two more examples. The third example is from the polymer electronics field, and in this case, they were looking at how polymers ordered themselves in thin films and how this was related to conductivity. In the fourth example, the group was looking at the morphology of waxes which crystallized on surfaces. There at the top are two kinds of different morphologies. with different waxes. And what they've found is that this morphology is more or less bactericidal. And these people, they use the ability of grazing incidence scattering to study the crystallographic growth of these morphologies as a function of time. So in this slide, I have the three basic scattering techniques that are used for determining structure. The first is specular reflectivity, and what one measures is the intensity of a beam of X-rays or neutrons as it's reflected from a substrate. Marate will go into detail about this technique and how one extracts information from it. But very briefly, one from the reflectivity curve as a function of Q, one measures the thickness of layers and their composition. Data analysis is done by comparing these specular reflectivity curves with a calculation based on a model, and one extracts the structural information by the model that correlates with what you actually measure. So this is a one-dimensional technique. It's only measuring information in the normal to the surface. Small angle scattering is a three-dimensional technique. One puts a sample in a collimated beam of X-rays, and one measures the dispersion of that beam as a function of angle. Again, data is used to get structural information, often by comparing it with a calculation based on a structural model. There are direct methods for getting structure from scattering curves, and we may talk a little bit about that later. But the subject of this course is grazing incidence or off specular scattering. The two terms are related. In some sense, they're not completely different. It's a hybrid of the two techniques. So we have a beam of X-rays or neutrons. It can be light, but we're not going to talk so much about that. And it interacts with a sample on a plane substrate, and we have an area detector which we detect the scattered neutrons or X-rays as a function of position on the detector. Let's focus a little bit more on that. So here's a larger schematic of the experiment. So we have a sample which is flat, which has some kind of morphology in the plane. We have a beam of X-rays or neutrons which interact at a very low angle with the sample, and at the back we can measure the number of X-rays or neutrons on a position sensitive detector. The incident angle, the angle at which between the substrate and the oncoming beam, is important, and it should be below the critical angle of the substrate. In fact, this angle here can modulate the depth in which the radiation probes the structure, and this detector can be further away or closer to the sample, which gives you, in the case of close up, larger solid angles or wider angles, and in the case of further away, where the solid angle is smaller, we look at larger structures. This will be a recurring theme. In the examples that I gave, we started off with the detector further away with the first example, that is the block copolymer structure, and the experiments considered much more smaller length scales by moving the detector closer to the sample. And again, this will be a recurring theme. I'll talk about that more later. Here is some instrumentation that can be used for these kind of experiments. This is a time of flight reflectometer, and the sample goes here, and there's an area detector where you can change the distance and the position to give you variable solid angles. This also uses wavelength, and this will be explained to you a little bit more later. This is a conventional SANS instrument. So the beam of neutrons is collimated. There's a sample here, and again, there's a detector behind the sample which we can move closer or further away to adjust the solid angle. At the bottom here, we have a powder diffractometer, which has been measured, been used to convert it into a reflectometer. We put the samples here. We have an X-ray tube here. The X-rays are collimated and interact with the sample, and we have a one-dimensional detector. I'll talk a little bit more about this later. Most of the actual data that we talk about in this course will come from this kind of instrument, where we have an X-ray source, collimation, the sample goes in here, and again, we have an area detector which can move further away or closer to the sample in this tank here. In terms of the analysis is that we're going to be using, we'll use different cuts of the detector, strips along the detector, to show different directional Q-dependent features. And in this case, we'll specifically have a lecture on using the PIT2D image manipulating program to extract those cuts, and we'll explain what I actually mean by cuts. We'll look at computing detector images and comparing them with the actual data that we have on the basis of the distorted wave-borne approximation. If you really like maths, there's a reference for you. The software that's used for this is called Born Again, for obvious reasons. And we'll also talk a little bit about how one optimizes the instrument configuration for the data analysis that you need to use. One of the recurring themes, or one of the many recurring themes here, is that we are able to focus on different levels of structure. And so with that very cursory introduction, I'd like to thank you for your attention. Please don't hesitate to contact me if you have any questions. And the next webinar will be given by Felix as a general introduction to small angle scattering. Thank you.